It's been a great few days hearing about research, but I like to think that we've left some of the best for last. So today's session is going to be on game theory and machine learning applications in security. And our first speaker is Bing Wei from Iowa State, and he's going to tell us how we can optimize our analysis of graphs for better performance in data-driven security. So let's welcome Bing Wei.
Hello. Hello. Thank you. Oh. Hello. Thank you for introduction. And my name is Bing Hui from the ECE department, Iowa State University. And this is a joint work with Jin Yuan and my supervisor, Neil Gong. First, what is the collective classification? Collective classification is a very powerful family of graph-based machine learning techniques. And in this talk, we only focus on the binary classification because that is always used in security and privacy problems. So let's suppose we are given an undirected graph or a directed graph. And we are given a training data set that consists of the labeled positive nodes and a set of labeled negative nodes. And the collective classification is to classify the remaining nodes to be negative or positive simultaneously. Studies from multiple research communities have shown that the security and privacy problems can be modeled as a collective classification on the graphs. For instance, in malware detection, we have a set of hosts, a set of files. And a host file graph is constructed between the host and the files. The positive means the compromised host or a malware. And the negative means a normal host or benign file. The age means that the host has the file. In SIBO detection on social networks, the graph is a social graph. And the node are users. And the edges are the following relationship between the users. And positive means that the user is a SIBO. And the negative means that the user is benign. And also in the attribute inference attack, the graph is also a social graph. And the positive means that the user has a certain attribute. And the negative means that it does not have an attribute. For instance, the attribute can be where the user lives in some city. And positive means that the user once lived or is living the city. And the negative means that the user does not ever leave the city anymore. So collective classification methods, as I said, have been studied by multiple research communities, such as networking, security, machine learning, and data mining. And roughly speaking, collective classification methods can be classified as a random walk-based and loopy belief propagation-based methods. These methods have three key steps. Step one, to assign the nodes prior scores based on a training data set. And they'll assign the weight. The weight can be fixed or equal to every edge in the graph. And then they will obtain the node's posterior scores by propagating the prior scores among the weighted graph. And a larger posterior score indicates that the node has higher likelihood to be positive. So different collective classification methods will use different steps. However, the fundamental limitation of the collective existing methods is that they assign the small weights to the homogeneous edge. What does that mean? A homogeneous edge, let's say UV, means that the U and the V should have the same label. However, and they should have the large weight. But existing method will assign small weights. It will also assign the large weights to a large number of heterogeneous edges. Heterogeneous edges means that the two connecting nodes should have different labels, and then they should have a small weight. So the existing methods will have limited success in the security and privacy problems that have a large amount of heterogeneous edges, such as SIBO detection in weak trusted social networks like Twitter. Based on this, we propose a framework that jointly learns the edge weights and propagate the posterior scores. And our framework is applicable to both random walk and LBP-based methods. And it is also applicable to both random undirected graphs and directed graphs. And it is also applicable to various graph-based security and privacy problems, such as SIPO detection, fake review detection, attribute inference, malware detection, malicious website detection, etc. And now the outline. We first showed the background of collective classification. In collective classification, the nose posterior scores are the solution to a system of the equations. Here, the Q means nose prior scores, and P means nose the posterior scores. And W is a eight-weight matrix that assigns a weight to every edge in the graph. And different collective classification methods, we use different function F. In practice, this linear system may be computationally expensive. So we always iteratively update the linear system using this equation. Now here, we first initialize the posterior score with the prior, and then we update the posterior scores using the posterior scores in the previous iteration and also the prior. Let's take an example. The loopy belief propagation on the undirected graph. The function f is here, defined as here. Basically, it says that the final posterior scores is the summation of the prior and the product of the edge weight matrix and the final posterior scores. And the nose prior scores are defined as follows. The LP and LN means labeled positive nodes and labeled negative nodes. And theta is a parameter that indicates the strength of the prior. It is a positive number. So it means that if a node U is labeled positive, we assign a positive prior. And if it is a labeled negative node, then we assign a negative prior. And for unlabeled nodes, we assign a prior 0. And for the edge weight, the edge weight basically means that the likelihood that the two connected nodes to have the same label. If the edge weight is bigger than 0, then we say that the two nodes are likely to have the same label. And if it is negative, then the connected nodes are likely to have different labels. So this is the setup. In LBP methods, it is always, the edge weight is always assigned to be a constant value. And that means we assume that all edges are homogeneous. Let's see a toy example here. We assign the prior score for the labeled symbol to the prior 1. And we assign a negative prior for the normal, for the benign user. And for the unlabeled nodes, we assign the prior 0. And then we will assign an equal edge weight for all edges. And based on this, we then propagate the scores among the graph and to determine the status of the unlabeled nodes. Here, the major issue is that we assume that all edges are homogeneous, and we assume the positive edge weights for all edges. And this is definitely not suitable for practical security and privacy problems. And this makes us to propose our method. The motivation. As I said, the existing methods will assign large weights or small weights to the heterogeneous edges or the homogeneous edges. So the question is, can we adaptively learn the edge weights such that the heterogeneous edges have small weights and homogeneous edges have large weights? This is the goal of this paper. To address it, we have two goals. The goal one is that we require the final posterior scores of the labeled nodes are close to the nodes labels. And then we quantify the goal using the function LW. Here the Y indicates the true label of the nodes. if the node L is labeled positive, we assign its label is 1. And if it's labeled negative, then it's -1. So basically, the LW function quantifies the difference between the true label and the final posterior scores. And from the machine learning perspective, the LW is also called the loss function over the training data set. And note that the goal one only use the labeled nodes. However, in practical problems, we have a great amount of unlabeled nodes. Then we propose the goal 2. The goal 2 requires that the learned age weights and the final posterior scores are constant. What does that mean? It means if U and V are predicted to have the same label, then the age should be homogeneous. And if U and V are predict different labels, then the age is heterogeneous. And then we quantify the goal 2 using this. That means if the product of the PU, PV is positive, then the age weight is positive. And if the product is negative, then the age weight is negative. And then we have the function CW, which is the product of the PU, PV, and age weight WVU. And our goal is to maximize such as the CW. And from the machine learning perspective, the CW is also called the regularization term. And then we have the following optimization problem that try to minimize this function. And also this is with the linear system constraints. This is definitely very hard to solve using some analytic methods. So we use the gradient descent to learn each edge weight. However, using some calculations, we found that to learn each edge weight WVU, we need to solve another linear system for each edge weight. And this is definitely very computationally expensive. So we need to find an alternative goals. And we found that the computational challenge is because we use the final posterior scores to quantify the true goals. Instead, we can quantify the true goals using the current posterior scores. What does that mean? It means if we are given the posterior scores in the tth iteration and the age weight matrix in the t-1 iteration, we want to learn the age weight in the tth iteration. And then we have an alternative goal 1 prime. That means the posterior scores in the t+y iteration of the label nodes should be close to the true labels. And the goal 2 prime means that the age weights in the tth iteration and the posterior scores should be consistent. Why would we do that? We will find the advantage of this. So we then have our joint weight learning and propagation framework. In step 1, we'll propagate the posterior scores to get the posterior score of the next iteration. And then we learn the age weight matrix in the tth iteration using the following object function. The first term is also the loss function that defined on the t+y iteration. And the second term is the regularization term on the tth iteration. And then similarly, we use the gradient descent technique. Also use some calculation, we found that the derivative of the posterior score with the edge weight is pt. Pt here, you see that is known. So in this way, it is computationally very efficient. The flow chart is as follows. We have an initial edge weight matrix and an initial posterior score. We use this to update posterior score P1. And then we use W0 and P1 to learn W1. And W1, P1 to update P2. And W1, P2 to learn W2, and so on. Because learning the posterior scores and the edge weight is jointly, so we said that it's joint weight learning and propagation. The evaluation. The application scenarios, we use two security problems and one privacy problem. The security problems are cyber detection and fake review detection. And the privacy problem is attribute inference attack. And we use the 4 real-world large-scale data sets. And we have the training data set. And we also use 3 evaluation metrics. We compared with state-of-art random walk and LBP-based methods for undirected graphs and direct graphs. And here is AUC Performance. The first table shows the results on undirected graphs, and the right table for direct graphs. And we see that our methods consistently outperform the existing methods. And this shows that the joint weight learning and propagation indeed can enhance the performance. And this is the visualization of the learned edge weights. And we see that the average edge weights between the positive nodes and negative nodes are decreased. And this shows that our method can indeed make the learned heterogeneous edges to be small. And the average edge weights between negative nodes and positive nodes are increased. This means that the heterogeneous edges are large. And scalability. We compare our method with state-of-art random walk and LPP-based methods. And our methods are only 2 to 3 times slower than the state-of-art methods. And then the conclusion, we propose a framework, and our framework is widely applicable. And iteratively learning can indeed enhance the performance, but with an acceptable computational overhead. That's all for talk. Thank you.
Bimal Vishwanath, Virginia Tech. Great talk. I have a question. So your method looks very sophisticated, and it looks like you have thought through how to handle some of these cases where regarding the edge weights.
I beg your pardon. Could you lower your voice because I cannot quite hear? Yes, sorry about that.
So can you hear me well now?
Okay. Yeah.
Yeah. So my question is, if you step back and think about the kind of networks you're applying these techniques to, right? These are real social networks, for example. And sometimes these edges are not so meaningful. So a lot of prior work in Sybil detection has shown that it is easy to farm links on social networks like Twitter. Like if you send a follow link to certain types of users, they will immediately follow you back. So when you apply these methods, how easy or hard it is to break your detection scheme?
First, I mean, the first part of your question is basically the direct graphs, the Sybil detection on direct graph, right? I mean, you said that
it can be directed or undirected, right? But
right. This method is applicable because in this talk I just showed examples on undirect graphs. In our paper, we also show the direct graphs. Okay. Yes, and for the second question, you mean how do you evade the algorithm, right? This is a very good question. This is basically the adversarial machine learning on graph-based techniques. Sure. I should say that for this method, I think it is very difficult to evade because the learning process is dynamic, and also because we need to jointly learn the edge weight and the posterior score. There are 2 different variables. We need to alternatively learn both of them. So if an attacker wants to evade that, he should know the iterative process of these 2 variables. But for the other graph-based machine learning techniques, it can be attacked. Okay. And also, in my group, we are currently focused on a project that attack the graph-based machine learning technique, and indeed it can be attacked. But for this method, it is very difficult because the learning process is dynamic. This is a very good question.
Hi, I'm Nikos from the University of Florida. Very nice talk. A very quick question. How do you show that your proposed method converges to a point?
Yeah, this is also a very good question. For this dynamic process, I think that there is no theoretical guarantee to demonstrate that this can be converged. This can be seen a drawback of this method, and because they have 2 reasons. The first reason is that as I said, it is a jointly learning process between W and P, And in this way, analyzing the convergence property is not difficult. Well, it's difficult. I once tried that and found that it is not so easy to analyze the convergence. Yes, I think this is the major issue that makes this iteration process cannot be guaranteed to converge. That's a very good question.
Okay, thank you.
Thank you.
Let's thank our speaker one more time.